Okay, so when I say the word Fortran, what pops into your head? Probably some dusty old textbooks, right? Or maybe those black and white photos of programmers with computers the size of a room? Well, what if I told you that this language born way back in the 1950s isn't just alive, it's actually one of the most important languages out there running on the fastest supercomputers in the world today. So how is that even possible? Let's dive in.
All right, here's the game plan for this explainer. We're going to trace Fortran's absolutely incredible journey. We'll kick things off by tackling the big mystery of how it's still around. Then we'll jump back to its revolutionary beginnings, map out its evolution over the decades, uncover its total dominance in a supercritical field, and finally show you why modern Fortran is, believe it or not, more relevant than ever.
So let's just get right to it. The big puzzle. We're in an industry where a language or a framework can feel ancient after just a few years. So how on earth has Fortran managed to stick around for nearly 7 decades?
I mean, let's be real for a second. Can something that was designed when computers filled entire buildings, can it really go toe-to-toe with the languages we use today? It just seems impossible, doesn't it?
Well, believe it or not, the answer is a resounding yes. As of early 2024, Fortran actually cracked the top 10 most popular programming languages in the world on the TOB index. This isn't some language that's just barely hanging on. It's actually seeing a huge comeback. The big question is, why? And to figure that out, we got to go all the way back to the beginning.
So, where did this all begin? Well, to really get why Fortran was such a big deal, you have to understand what a complete nightmare programming was in the early 1950s. Just try to picture this. You're a scientist, and you need to calculate something important, like a missile trajectory. Before you can even start with the math, you have to write these super complex, cryptic instructions that only work on the one specific computer you're using. Every single calculation was this monumental task, and one tiny mistake could set you back days. It was a slog.
And then Fortran comes along, and this was a massive, massive leap. It completely flipped the script. We went from having to speak the machine's language to making the machine speak our language. Instead of all those painstaking machine-specific codes, you could write something that looked, well, like a math equation. It was way easier, way faster, and for the very first time, your code was portable. You could run it on different computers.
And you want to know the best part? The motivation for this brilliant, world-changing innovation was beautifully simple. John Backus, the guy who led the team at IBM, he said it himself. He was lazy. He just hated how tedious assembly language was, so he invented a tool to make his own life easier. It's just a perfect story of innovation being born out of wanting to find a smarter, not harder way to work.
And really, its whole purpose is baked right into that original name, the Formula Translating System. Its goal was never to build operating systems or websites. It was built for one reason: to let scientists and engineers focus on science and engineering without having to become low-level computer wizards. But, coming up with a revolutionary language is one thing. Keeping it at the top of its game for 70 years, that's a whole different story. Fortran didn't survive by staying the same. It survived because it never, ever stopped evolving.
I mean, really think about this for a second. The first Fortran programs were literally punched into physical cards. And there were all these rigid rules, like column 1 was only for comments, columns 1 to 5 for labels, column 6 meant you were continuing a line. Your entire program was a physical deck of cards. If you dropped them, you were in for a very, very bad day.
And this journey from those punch cards is the key to its survival. Fortran 77 brought in structured programming. Then Fortran 90 was this huge leap forward. It got rid of the fixed columns, added powerful array operations. From there, it just kept going, adding object-oriented features in 2003, and then, this is a big one, native parallel programming in 2008. The point is, the language never stood still. It just kept adapting.
So, this constant reinvention is a huge piece of the puzzle, but it's not the whole story. The real secret to why Fortran is still here is that it became the absolute, undisputed king of one massively important field. And that field is high-performance computing, or HPC. See, Fortran wasn't just good at number crunching, it was literally born for it. Its compilers are legendary for how incredibly fast and optimized the code they produce is. So when raw speed is the only thing that matters, Fortran is almost always the answer. And we're not talking about small stuff here. This is the language that predicts hurricanes, that helps design airplanes, that simulates black holes colliding. It models the fundamental building blocks of the universe. These are literally some of the most complex computational problems humanity has ever tried to solve. and they run on Fortran.
Let me put it another way. When you want to find out which computer is the fastest on the entire planet, you test it using a program written in Fortran. It is, quite literally, the gold standard for pure, raw computational power.
So that brings us to today, and it's time to just completely demolish this old idea that Fortran is some clunky, outdated language that's a pain to use. Because that couldn't be further from the truth.
The reality is, thanks to an amazing and passionate open-source community, working with Fortran today feels just like working with any other modern language. The days of cryptic tools and weird workflows are long, long gone.
I mean, just look at the ecosystem. You've got tons of incredible compilers to choose from. You can write your code in VS Code with all the fancy syntax highlighting and auto-completion you'd expect. It's got its own modern package manager, FPM, to handle all your dependencies, and it plays nicely with standard tools like CMake.
And the language itself is totally modern. We already mentioned coarrays for parallel programming, but it also supports object-oriented and even functional programming styles. It can talk to C code seamlessly, and it's got all the features you'd expect, like dynamic memory and structured data types. This is not your grandfather's Fortran.
In the end, this quote from the physicist Cecil Leith just nails it. Fortran isn't just a language for science, it is the language. It really is the mother tongue. It created the patterns, the libraries, and the very foundation of how we use computers to explore and understand our universe.
And that leaves us with one last pretty fascinating thought. For nearly 70 years, this language has been the quiet engine behind some of the most important scientific discoveries of our time. So, with all this new energy and constant evolution, the only question left is, what monumental challenges is it going to help us solve in the next 70 years?